This talk is about work on symbolic cross-checking on floating point and SIMD code. I'm Peter Collingbourne. This is joint work with Christian Kadar and Paul Kelly. So today I'm going to first of all talk about what SIMD is, then give an overview of symbolic execution, talk about CLEFP, our extended version of CLE. Then I'll talk about how we evaluated our technique using an open source computer vision library which contains SIMD as well as scalar implementations. So what's SIMD? SIMD stands for Single Instruction Multiple Data. It's a popular means of improving program performance. In what we do is we operate over one-dimensional arrays of data known as vectors, and in this example we're taking the two 4 wide vectors of floats A and B, and we produce vector C by multiplying each element pairwise. So an issue with symbolic execution is an issue with SIMD is that manually translating scalar code to SIMD code is generally a manual task unless you're using an automatic vectorizer. It's difficult and error-prone. It's easy to make a mistake. But we propose an automatic technique that for verifying that SIMD code is equivalent to the original scalar code. So symbolic execution is a means of testing a program. We test multiple paths through the program. We determine feasibility of particular paths using constraint solver, and we verify code correctness by checking for various error conditions such as array bounds or division by 0. For example, if we're checking for division by 0, we can ask the constraint solver whether the denominator can ever be 0, and we do this on a per path basis. So the way symbolic execution works is we essentially execute the program except with variables which may contain concrete or symbolic values. An example of a concrete value is 2. A symbolic value is made up of symbols and could be something like x plus 3. So this is an example of how symbolic execution works. On the right we have our state, and initially we start with x having an undefined value. Then we assign x a symbolic value, so it gains the value x. And what happens next is that we reach this assert statement, which actually expands to something similar to the if statement underneath it. So you might think, oh, x is always going to be greater than x minus 1, so the false path will never execute. But in fact, what we do is we fork execution, which is what happens when our constraint solver tells us that both paths are feasible. So the reason the false path is feasible is if x is 0, you get an underflow if you subtract 1. And so we reach both paths and we abort. So let's add an if condition there. And what we do is we make it symbolic again, and when we reach the if statement, we fork our execution again. We reach the if statement, and what happens is our constraint solver correctly determines that the second execution path is infeasible, and we eliminate it. So issues with SIMD and symbolic execution. So SIMD vectorized code often makes use of floating point, but we are unable to find a tool in the current generation of tools which adequately had support for both floating point and SIMD. So this is the problem we tried to solve with this work, and the technique we use is for cross-checking. So for cross-checking, you're testing a scalar version of the code against a SIMD code. And so for the purpose of this work, we only need to test equality. So it's harder to satisfy an equality constraint for a floating point value than it is for an integer, mainly because of the higher granularity of floating point values. Usually we need to build the two numbers up in the same way to be sure of equality, and that's exactly what we do for our verification technique. So CLE is the tool we extended. It's a tool for symbolic testing of C and C++ code. There's a paper on it by Christian Kadar, Daniel Dunbar, and Dawson Engler at OSDI. It's based on LLVM. It's open source, but it only supports integer constraints. No floating point, and no SIMD either. So these are our improvements to CLE. We added a symbolic construction of floating point operations. We added a set of expression matching and canonicalization rules, and we're going to be looking at one of those shortly. Support for the SIMD LLVM instructions, and we define a semantics for a substantial portion of int LSSC, and we're also going to be looking at how we defined those semantics. We also, in the course of this work, made some contributions to LLVM, namely atomic intrinsic lowering and a more aggressive variant of finite folding, and we'll also be looking at those later as well. We tried to contribute upstream as much as we could, and this work is also open source, and you can get it from that URL. So, just to show you a scalar SIMD implementation of a particular routine, this routine takes the source array, and for each element of that source array, it checks whether the value is greater than 0. If so, it copies the value from the source array into the destination. Otherwise, it places a 0 in the destination array. So there's a scalar and a SIMD implementation. So let's look at the SIMD implementation first of all. So you start with, so the way it works is you have the a greater than comparison, which is which compares each element of source v pairwise with the elements of 0, 4, which just contains zeros. And what we get back in comp v is a bit mask, and that bit mask consists of all ones if the comparison resulted in true, and all zeros if it resulted in false. And so we just do a bitwise AND of the original source vector with the comparison vector to produce a destination vector which has all the non-positive numbers replaced with zeros, which is also the floating point representation of positive 0. So this is what the tree, the way CLE works is it builds expression trees, and this is what the expression tree looks like for the first element of the destination array. You can see there's a greater than operation, sign extension, which extends the 1-bit outcome of the greater than operation to 32 bits. We also have read LSB, which just represents the read from the source array. So that's the scalar implementation. It's much simpler, as you can see. And that's the expression tree. We have select, which represents a ternary select operation. That's the only new thing. We again have the comparison and the array read. So these are the two expression trees again. And what our tool does is we employ one of these transformation rules at expression construction time. And what that actually does is it converts the first tree into the second tree. And the whole point of that is that later on we'll need to compare those two trees, and if they're using a simple tree comparison, and if they're equal, then if we can show that the two trees are going to be equal, then we can eliminate the false path for that particular condition. So this is our test benchmark driver, and all we do is we create a symbolic array source, which covers the input array. We run the z-limit routine in both scalar and SIMD modes, which is what the first parameter is. We loop over the two output arrays and we assert that they're equal. Note that we are in fact comparing using a bitwise comparison, using a straightforward pointer bit cast. So we end up. So the reason for this is that in fact you can construct two floating point values which actually compare. The comparison operation of equality returns false even if the two operands are equivalent, and that's the case where you have nans. So to make sure that doesn't happen, we just do a bitwise comparison. So this is how we handle a more complex case. The expression at the top there is an example of an expression you might encounter in the false branch of an assert statement. We want to simplify it so it only contains integer expressions. That's because the constraint solver we use, in fact, there aren't any floating point constraint solvers that we know of that are capable of being used in this fashion. So we use an integer constraint solver, so we need to simplify our expressions for the integer constraint solver. So we just identify the integer sub-expressions in the input expression where the two trees are operands of an equality comparison. We end up with this, which just consists of integer expressions, and our constraint solver will be able to show that in fact that condition is in fact infeasible, and we can eliminate that path. So to support floating point operations, we added 12 new operation nodes, which cover floating point arithmetic, conversions between floating point and integer values, conversions between floating point precisions and a floating point comparison operation. We added a concept of outcome sets for the purpose of the floating point comparison operation. This was in order, as you'll see, this was in order to help us simplify the floating point comparison operations. So on the left we have shorthands such as an ordered equality, which is a straightforward equality comparison, and we borrowed the representation from LLVM. So the second column just represents ordered equality, and then we have the comparison operation, and essentially that's just what we did. We just represented it in that way. So expression transformation rules. These were our 18 rules, and the top 3 rules show how we can use the outcome sets to simplify Boolean operations over floating point comparisons. The 4th and the 5th rules show how we can simplify floating point equality to integer equality, and that's important for some of our benchmarks which use floating point equality in the scalar version and integer equality in the SIMD version. So we needed a rule for that. And the 6th rule we've already seen. So category analysis. And this was our technique for doing a simple kind of interval analysis over floating point values. We establish a category set which contains not a number, negative infinities, negative numbers excluding negative zeros, which covers positive and negative 0. We have positive numbers excluding 0. We have positive infinity, and we categorize each floating point value falls into one of those 6 categories. We establish a set of rules which are used to derive the category set for any given floating point expression, such as if x and y are known to be positive, then the result is going to be positive or positive infinity because of in case you have an overflow condition. And we use those rules to say things like, if we know that the left-hand side of a greater than comparison is 0 or negative, the right-hand side is 0 or positive, we know that x is greater than y is infeasible. So intrinsic lowering, this was how we handle SSC instructions. We support out of however many SSC instructions there are, we support 37 of those. We implemented it using a lowering pass that translates the intrinsics into standard LLVM. For example, PSLLI is an instruction that takes vector and shift operand, and the shift is used to shift every element of the input vector. And as you can see, we just have straightforward extract element, shift left, and insert element instructions to build the output vector res. So finite folding, and this was our technique for supporting certain benchmark codes that looked like the code at the top there. And what that code actually contains is a nested conditionals. So the way we handled that was, the way that this compiles to LLVM is shown below, and And there's actually, on the last line, basic block 156, we have a branch, and the operand of the branch is in fact silhouette data of X, and that is actually a symbolic input. And so we fork. And the problem there is that this fork happens once for every element of the input array. And as you can imagine, if that input array is quite large, we run into problems. So our extension to the finite folding mechanism simply allows us to convert the phi node at the bottom there into a straightforward select statement. The advantage is that you have a straight line execution, and you end up with something like this. So you have a straight line basic block 156, and that essentially contains the full implementation of the code you saw on the original slide. And so the advantage of this is, for example, for a 13 by 13 matrix, we started with 2 to the 169 forks, and we went down to 1. As you can probably imagine, that's quite a significant improvement. So for our evaluation, we looked at a set of benchmarks which we developed that compare the scalar and SIMD code of a particular open source computer vision library. We didn't develop it ourselves. We didn't make any changes apart from those which were necessary, which weren't very significant. The code base is OpenCV. It's a popular C++ computer vision library, and underneath you can see an example of a line detection algorithm in OpenCV. So for our evaluation, we selected out of the 20 OpenCV source files with C code, we selected 10 of those, and we built benchmarks on top of them. And those benchmarks essentially look like the example code I showed you before, which calls the scalar version of the code and the SIMD code, and then just loops through the output array and compares the arguments with an assert. So we looked at 49 implementations, which is to say we had various implementations. OpenCV contains various implementations for different input formats, for different algorithms, which were subtly different. So there ended up being 49 of those. We managed to prove the bounded equivalence. That is to say, the bounded equivalence means that we verified the equivalence for matrices up to a certain size due to constraints associated with symbolic execution, and those are fundamental constraints. We can't supply symbolically sized matrix, so instead we used fixed matrix sizes and went up in size until various constraints stopped us from going any further. And we ended up finding inconsistencies in the other 10 implementations. So these are our coverage results. Each coverage number represents the coverage of SIMD instructions within each individual source file. As you can see, we hit 100% in quite a few source files, but for the other source files, we ended up having to omit certain code, which was simply an unrolled version of the original SIMD loop due to various constraints. We couldn't cover the whole code. We couldn't. That is to say, we couldn't test certain array sizes above a certain size, and so the lower coverage numbers simply represent the unrolled code we couldn't cover. So this slide isn't so much meant for you to read, but it is meant to show how many different benchmarks we covered and how many different algorithms and different size formats. In some cases, we went up to 20 by 20 matrices. In other cases, we were very limited by execution time, and we could only test a very small matrix, which was the smallest possible size that could invoke the actual SIMD code. These were the mismatches we found. We found 10 in total. On the right, there's a small description of the error we found. It was mainly due to human errors, like getting the associativity wrong or not memorizing the myriad rules for implicit conversions. There's one where one algorithm was written as an integer computation, and the other one was floating point. The entire computation was done this way, so it couldn't really handle it at all, really. So just to give you an example of one of these errors that we found, which was the ordering issue with min and max operations. So at the top there you see the standard implementation of min and max, which is used in the STL library as well as in the SSE instruction set. Underneath that you see that min is in fact not commutative, and you can see underneath that it's not associative either. The reason it's not commutative is that if one of the operands is nan, then the less than comparison will always evaluate to false, so you always get the right-hand operand. So as you can see, it's not associative, and if we substitute some values in, we see that we get a completely wrong result if one of the operands was nan. You're getting instead the maximum rather than the minimum. So, conclusion, we've shown how ClearFP extends CLE with floating point and SIMD capabilities. We've used it to find bugs in code we extracted from the wild. We're looking at various future work. We're looking at solving inequalities using either interval arithmetic or another technique known as affine arithmetic. We're looking at ways to find floating point counterexamples, because all of the counterexamples we found we found them by essentially thinking about what those counterexamples would be, and it would be nice to be able to automate that. We are also looking at cross-checking of GPU code against CPU code. So OpenCL is the language we're concentrating on at the moment, and we're writing an OpenCL implementation using Clang that's integrated into CLE FP that we can use to cross-check GPU code in the same way, essentially the same way as we've already seen for SIMD code. So that's it. There's the URL again.